Hi guys, in my previous concept I covered magnetic field due to a circular loop at an axial point or along its axis. So the magnetic field at point P, so we derived the magnitude of magnetic field B equal to mu naught I a square upon 2 times r square plus a square whole power 3 by 2. So here a equal to radius of loop and I equal to amount of current in loop, and R is the point where we need to find the magnetic field, a location point. So a small change, suppose this loop is made up of so many turns. So if we make loop one over other like that, with so many turns, if loop contains capital N number of turns, usually coils cannot make with a single turn. So a coil is made up of number of turns. So instead of taking one loop, if you take a coil, a current carrying coil, which contains capital N number of turns. So that formula changes, the formula at here will changes, B bar equal to mu naught capital N I a square upon 2 times r square plus a square whole power 3 by 2. And magnetic field is a vector, so we need to represent the direction. So here the direction vector is along the x-axis direction or towards east. So unit vector in the x-axis goes to I cap. So from this, if you want to find the magnetic field at the center of the loop, exactly at the center, so magnetic field at the center, so in this case the value R equal to 0. So if you can plug in this formula at there, so this formula will be converted as B bar equal to mu naught capital N I upon 2a times I cap. So this formula gives the magnetic field at the center. At the center of the loop. So magnetic field is a direction dependent quantity. So to find the direction, so we need to use the right hand thumb rule. For a given loop, suppose this is a given loop, so the current in the loop is along counterclockwise direction. Now according to this rule, if we curl our fingers in the direction of current, curl our fingers in the direction of current, curl fingers in the direction of current, and extended thumb indicates the direction of the magnetic field. So here thumb, which is indicating in the direction of magnetic field. So this we can use with the right hand, so that's why it's called as right hand thumb rule. So the right hand thumb rule will help us to find the direction of the magnetic field in the given coil. So curl the palm of your right hand around a circular wire with the fingers pointing in the direction of current. So the right hand thumb gives the direction of magnetic field. So this is how to identify the direction of magnetic field. So this is a simple rule to find the direction of magnetic field. All need to care about, we need to curl our fingers in the direction of magnetic field, and extended thumb, we need to curl our fingers in the direction of current, and the extended thumb shows the direction of magnetic field. Or we are having one more loop rule. Suppose if I take loop, so in this loop, if the current is flowing in this direction, counterclockwise direction, since magnetic field having two poles, yeah, magnetic field is two poles. One is south pole, second one is north pole. So if this coil is carrying current in this direction, counterclockwise direction, which pole it indicates? So to draw that, just draw in the same direction. Just you draw either N, a letter N, or follow the arrow mark. So if I draw the N at here, so the top is carrying the same of the direction of current which at here, and the bottom, so this is also indicates the same in the direction of the current. So these two are something similar. So now if current is flowing in a coil counterclockwise direction, now that coil contributes magnetic north pole. So now nothing, just to draw a letter N and try to match it if that arrow marks are matching at the same time or not. Or you can remember like that, if current is in counterclockwise direction, that coil contributes north pole. Similarly, if you take a coil which is flowing current in clockwise direction, so now let me take the current in this clockwise direction. So this is clockwise direction. Now in this case, just I write the letter S. Now I will give the arrow marks now at here. These two arrow marks are same at here, and this is also will be same. Now you can make your own shortcut to remember. Now this loop will be act as magnetic south pole. So from this we can conclude that if current is flowing in a coil in counterclockwise direction, now that loop will be acts like magnetic north pole. Or if current is flowing in clockwise direction in a loop, now that loop will be acts like magnetic south pole. So apart of that, I would like to encourage you to remember this loop, right hand thumb rule, because this always we used to use whenever the situation needed, especially in the problems. So without direction, magnetic field is incomplete concept. We need to find the magnitude very easily by using the formulas, but we need to specify direction too also. Now let us try to find one small simple problem. So the problem is given in our example problem only. So the problem says, consider a tightly wounded 100 turn coil of radius 10 cm carrying a current 1 amp. What is the magnitude of the magnetic field in the center of the coil? So a coil which is made up of 100 turns. So let me consider a coil, so which is made up of 100 turns. Therefore N, capital N here equal to given 100 turns, and current in the coil which is given 1 amp. You can take any direction. So suppose if you take the counterclockwise direction, let me take this is the direction of current to specify the magnetic field direction. N equal to 1, and the radius of the coil. Suppose if it's center, from center to radius, the radius value they are given that the radius R equal to, in the formula I have taken that radius equal to A equal to 10 centimeter. So A equal to 10 centimeter, we will convert that in terms of meter, that is 0.1 meter. And we need to find the magnitude of the magnetic field at the center of the coil. Only magnitude it's asking. So don't bother about the direction. So we can use formula magnetic field B equal to mu naught n I upon 2a. I think if memory is correct, yeah, it's 2a. Mu naught n I upon 2a is the magnitude of magnetic field at the center of the coil. So here a is the radius, I is the current, and n is the number of turns, and mu naught is the permeability. So let's substitute the values. Mu naught value here given 4 pi times 10 power minus 7. So we can take that mu naught value as mu naught value here equal to, if I write that, mu naught equal to 4 pi times 10 power minus 7. So substitute all the values and do the calculation. So here it is 4 pi times 10 power minus 7 times n equal to 100. Current I equal to 1 amp upon 2 times A equal to 0.1. So I would like that 1 times 10 power minus 1. 1 times 10 power minus 1. So let's simplify this, then try to get that value of what is the magnitude of the magnetic field. So if we can cut this simple 2 times, so that will be end up B equal to 2 pi times 10 power minus 7 times, if we can take 10 power minus 1 numerator, that will becomes 1000 altogether. Now if we can do for the simplification, this is 2 pi times 10 power minus 7 times 10 power 3. So final result will be equal to 2 pi times 10 power minus 4 Tesla. So this is the magnitude of the magnetic field. So since I have taken direction, you can specify the direction also, whether it is along the x-axis or y-axis. So for that you just curl our fingers in the direction of the magnetic field. So if I curl the fingers in the direction of the magnetic field, now the resultant direction of the magnetic field, we need to curl the fingers in the direction of current. So note that carefully, always I am spelling about that, curl the direction of the magnetic field. That was wrong sentence. Check it out, that curl your right hand fingers in the direction of current in the loop, and the extended thumb gives the direction of the magnetic field. So let's try one more problem. Two small identical circular loops marked 1 and 2 carrying equal currents are placed with the geometric axis perpendicular to each other as shown in figure. Find the magnitude and direction of the net magnetic field produced at point O. So this is a given point O. So write it here. We need to find what is the magnitude of the magnetic field and the direction. So same current is flowing, and to these two coils, so the point O is the location of an axial point. They both are at equal distance. So for the magnitude, we can write that for the first coil B1 equal to, so mu naught n I a square upon 2 into a square plus r square. But here distance r equal to x, so we can convert that 2 into a square plus x square whole power 3 by 2. Now for the second coil, so just I am writing magnitude, so I can put modulus. So modulus of for the second coil B2, so at point O also an axial point to the second coil, B2 equal to, so mu naught n I a square upon 2 into a square plus x square whole power 3 by 2. So here x is the location of point where we find location of O from each coil, and a equal to radius of the loop. Now we got it magnitudes, then okay. Then we need to find the direction. So to find the direction, so I will use the right hand thumb rule or right hand rule. So the right hand rule says curl our fingers in the direction of current. Curl our right hand fingers in the direction of current. Then the extended thumb gives the direction of magnetic field. So the figure and the coil 2, they both are same. So easily I can get the resultant magnetic field. From this I can get the resultant magnetic field, so along the upward direction. So at point O, the resultant magnetic field is along upward direction. This is from B2 coil, from the second coil, that is magnetic field due to second coil. And from the first coil, what is the direction of magnetic field? So if you can curl if the right hand rule, so just like in the previous problem, so the direction of magnetic field shows along inside directions. It means it will become, if I can draw the vector at here, so it will show us along in this direction, on the same axis direction. So this is magnetic field direction due to B1. Now magnetic field is a vector, B is a vector. So here two magnetic fields are acting at the same point. They should be resultant magnetic field. So the resultant magnetic field will be acts in this direction, that we can be add up by, or we can calculate by using triangle law of vector additions. So here you can use the triangle law of vector addition to find the resultant. So this is the resultant magnetic field B due to both magnetic field due to B1 or first coil, or magnetic field due to second coil. So this angle is making an angle of the 45 degrees. Now to find the resultant magnetic field, the magnitude will be changes. So as magnitude of B1 is perpendicular to, not magnitude, just B1. Magnetic field B1 is perpendicular to magnetic field B2. So they both are direction. So the net field. So the net field B equal to square root of B1 square plus B2 square. So here we use the triangle law of vector addition. So just multiply that and we can apply what we are already having the magnitudes, and we can get that square root of mu naught n I a square upon 2 times a square plus x square whole power 3 by 2 plus mu naught n I a square upon 2 times a square plus x square whole power 3 by 2. Now let us do the simplification. So if we simplify this, b equal to square root of 2 times mu naught n I a square upon 2 times a square plus x square whole power 3 by 2. So let's cut what are the like terms. So here the 2 gets cut, cancels. So let it be that the rest of the terms b equal to the magnitude be equal to under root mu naught n I a square upon a square plus x square whole power 3 by 2, or I would like to represent that under root as whole power 1 by 2. So we can take the whole brackets and I can write that as whole power 1 by 2. So here it is little a. So this is the magnitude of the magnetic field due to the current carrying coil when they placed exactly perpendicular to each other.